point to determine for example, purity. You can still use a melting point. You make a new compound in the research lab and it's brand new, you don't want it to be on 500. You want it to be. You want to be the first one to report a melting point, etc. Some of you have used Acyl Anhydride in lab. Yeah, is that right? Mm-hmm. To make an acetamide, an amide from Acyl Anhydride. In the workbook, there's a little information on this page about morphine making heroin. Heroin, yeah, it was on the previous page, right? Heroin is diacetyl morphine. Acetyl groups come from acetic anhydride. Acetic anhydride is a liquid. It's very big on the so-called black market because you can convert morphine to heroin using acetic anhydride. You should know the chemistry. Please take a look at that page, including anything else in the workbook. Okay, what else can we say? We have a handout for the next, for down the road a little bit. Blue handout. We need to get going. Chemistry of acid chlorides. Acid chlorides, also called acyl chloride. Acid chlorides are reactive intermediates in the lab. They're never going to be final products, never going to be a drug. They're too reactive. Never going to find them in nature. They react with water, no catalyst needed. Okay? We can get an acyl substitution. Water acting as the nucleophile, coming in here, electrons up. Okay, and we can just place the chlorine, and the H that's there is taken by the Cl minus for everything to go neutral, and you'll generate HCl. You can do this with an alcohol. Do this with alcohol, you're going to end up with an ester. And the chlorine will take the H from the oxygen during the mechanism. Pretty straightforward, no catalyst needed. Of course, you can also do this with hydroxide. That's hydroxide. Up there, water is reacting as the nucleophile. Down here, I'm showing this with hydroxide. And if water can be a nucleophile, so can hydroxide. Okay? And so electrons just come in and add, and electrons up. Sometimes we'll do this going forward, okay? Electrons up, what's next? Electrons back down, kick the chlorine off. Okay? You can't do that on quiz or test though. This is just me showing you, right? Sometimes you'll see it done like this, sometimes maybe in the workbook. Okay? I'm just sort of combining lots of things here. What do we get here? Well, you just an acyl substitution, right? Boom. We now have an OH there. Is that the product? No, we're under hydroxide. Basic conditions. It's going to be deprotonated, right? Hydroxide will take an H. This is the end step 1. And then what's the purpose of the H plus workup?
Put the H back on.
Put the H back on. Okay? Let's see here. Reactions with amines. C, I imagine we're under acid chlorides, reaction with amines. Very common reaction to get an amide. Simplest amine would be ammonia, acid chloride. Nucleophile, come in, electrons up, right? Electrons can come back down, kick off the chlorine. What do we get? Boom, boom, boom. That would be NH3 here. Then what can take an H here? Okay, Cl minus. These electrons take the H, leave these behind, and we get our product, acyl substitution. We now have a nitrogen on the carbonyl instead of the chlorine. This is going to cause problems. We generated HCl. Problems with this. Why is this a problem? Because you have a base here. Amines are basic. If you generate acid, this is going to be like, oh, I like you, acid chloride. No, hold on, I like acids even better. I'm going to go react with that generated acid. Acid-base reactions are instantaneous. That's going to be the problem. You're going to destroy this. Okay? How can we deal with the acid? We can use two equivalents of amine. Okay? Use two equivalents of ammonia. One to fully react with this, and one to fully react with that. And if you use two equivalents of ammonia, I'll go ahead and change this. If we use two equivalents of ammonia, what are we going to generate over here? Not HCl, but ammonium chloride. Okay? One ammonia reacted with the acid chloride, another ammonia reacted with acid HCl. You can get ammonium chloride by ammonia reacting with HCl, or you can show ammonia taking the H here. If the ammonia took the H here, you would have ammonium, and the Cl minus would just sit with the ammonium. Alternative is, if you don't want to use two equivalents, if you used ammonia, you'd probably use two equivalents because ammonia is very cheap. It's actually hard to weigh out anyway, so you just sort of use excess. If this was some amine that was like maybe expensive, you would not want to use two equivalents. Instead, maybe you use your amine and you use some other amine, such as triethylamine or pyridine, to take care of the HCl. All right? You'd only use two equivalents if your amine is sort of cheap and easy to get rid of. An alternative is to use something. Okay, so we can show products down here. This is the acid chloride of benzoic acid. It's called benzoyl chloride. React this with, what, can you show a product here? Can somebody name your product? Nomenclature. Somebody have a name of your product? N-methylbenzamide, yes. N-methylbenzamide. Your amine displaces the chlorine, right? But you're going to lose an H from the nitrogen to go neutral. What's going to take the H? Well, we use two equivalents. Methylamine is a stronger base than Cl minus. Have methylamine take the base. We're going to make that plus that ammonium chloride. What's the purpose of the second equivalent of the base? To react with HCl that might otherwise have been generated. Right? We use two equivalents. Yes. Benzamide is the amide of benzoic acid. It would be called benzamide. N-methylbenzamide. Yeah, amide. Acyl substitution, using an acid chloride to make an amide. Very common. Down here, this is the acid chloride of acetic acid called acetyl chloride. Very common. Some people say acetyl. And in fact, it's kind of, both are used, kind of like Caribbean and Caribbean. Acetylsalicylic acid, aspirin. Otherwise, I would probably say acetyl. That's what I say. I say both. I like acetyl. Acetyl chloride. Acetyl chloride, I say both. Very common. Product here. Note the difference. Here I've got an acid chloride as the main here, and I got the amine on the line. Here I got the amine here, and I got the acid chloride on the line. Doesn't matter. No, they're both in the same flask. Okay, just different ways to show it. You got to assess reactivity here. Very reactive acid chloride. Acyl substitution. Got a good nucleophile here. Product. There's no memorizing this. These electrons, here's your nucleophile, right? What else is the nucleophile? Neutral halogen is not going to be a nucleophile. These electrons in, electrons up. We can bring them back down, kick this off. Again, I'm doing shorthand here. You can't do this on quiz or mechanism. It's stepwise. Okay? This thing just saves us some ink, saves us some time. We're going to lose an H here. What's the purpose of the triethylamine?
To not interact with the chlorine.
Triethylamine is an alternative base we can use instead of using two equivalents of the amine. Would you want to use two equivalents of this?
No.
One to react with the acid chloride and another one of these to just act as a base? No, this is too big of a molecule. What if it took you 6 months to make this? Would you want to use half of it just to act as a base? That's a big waste of your. Let's bring in another base. Let's just use one equivalent of this and bring in a cheap base like triethylamine. Product here is nitrogen now bonding to the carbonyl. There's an H here. There's an F here. Is that the product? Basically, under my hand it used to be chlorine, but now it's what? The nitrogen. And we're going to lose an H. What's going to take the H? Well, triethylamine is going to have it. You'll have Cl minus. You'll make this ammonium chloride. Something's going to take that H. You'd rather it be triethylamine take it than you're starting amine, which may be expensive or otherwise very valuable. Use of triethylamine to act as an acid scavenger. What type of product do we make? Yes, it's an amide. What type of amide is that? It's an acetamide. Acetamide, acetyl group. Acetamides. Very common type of simple amide. We made the acetamide by reacting the amine with acetyl chloride, or acetyl chloride.
Mr. Stevens,
Uh-huh.
is the triethylamine going into the flask at the same time as the starting base? Is it everything's going in all together?
Yeah, why would you think that?
Because I'm thinking, how do we know for sure the triethylamine? Never mind.
No, come on.
How do we know for sure the triethylamine is just going to react with the chlorine and not anything else?
It doesn't react with the chlorine. It reacts with the, because at some point in the mechanism you have two H's here.
Yes.
Something has to take that. Cl minus will take it and you can generate HCl.
Okay.
If you generate HCl, then this is going to react with HCl and it will no longer be able to react with the acid chloride.
Got it.
So triethylamine will react.
Okay.
But I thought you were going to ask a question.
There's a question I want to ask, but I can't formulate it right now.
Why does the triethylamine not react with the acid chloride?
Yes.
Was that the question?
Yeah. How do we prevent that? I would think we would have to do it after that reaction happens. Our wanted reaction.
First off, this is all together now because we didn't do anything like 1 and 2.
Okay.
We did 1 and 2, that means separate. That means this is done 1 week and then next week you come in and you do this.
Right.
We didn't do that. Everything's in the same flask.
But we want our big base to react with the acetyl chloride, right? That's what we want to happen.
Or a nucleophile. Triethylamine. Okay, let's talk about triethylamine. This is a primary amine. This is tertiary. Is this going to react here? Is this a good nucleophile? Good nucleophile. It's not great because it's sterically hindered. And indeed, when we first introduced triethylamine in Organic 1, we introduced it as a sterically hindered base for doing E2 eliminations because it wouldn't do substitution because it's sterically hindered. Look back at the Organic 1 handout.
Okay.
Triethylamine is a decent base for E2, sterically hindered. Okay? So you're asking, can it react here? Actually, it can. But if it did, okay, this is free information, it's going to blow your mind, but what would we get if triethylamine displaced the chlorine? Would we get that? Triethylamine has displaced the chlorine by an acyl substitution mechanism. How are you going to go neutral? There's no H to lose. So actually at this point, then this can come in here, up, down, and kick that off.
So we still get.
You still get the same thing. And
So
it's
that
actually,
could happen, then it's
this
possible.
could theoretically happen, and a lot of times, okay. So the fact that it's a tertiary amine means you're not going to make an amide. What did I say? A base that will not react with the acid chloride, and then I'm like, uh-oh, it might to give an amide. Triethylamine will not give an amide here, because this is not going to be isolated. Then this could come in and just kick that off. So, good questions. There's some practical details along the way.
Is the charge intermediate efficient and strong enough to do EAS?
Is the what?
The intermediate you just erased, is it strong enough to give an EAS product?
You talking about the ring here?
Yes, sir.
Reacting with what?
The charged nitrogen and attacking the carbon beneath it, kicking off the acetamide?
An internal reaction?
Yes, sir.
Possibly, but in general I'd say no.
Okay.
There's lots of chemistry that's possible to question. I thought you were going to ask, could we do like a Frito Crafts with the ring? We got an acid chloride. The thing here is, there's no way, if you had seen something like this looks like ring acylation Frito Crafts. The problem here is, what's the big problem here? You got an amine here. This is going to make an amide. If we got rid of this, then, and added this, now it looks like we're doing a Frito Crafts, and now we can say, okay, ortho-pair directors or whatnot. But we don't. We've got, this is the chemistry here. Okay, base. As we learn more, we actually have to think more, because now we have multiple possibilities. Okay, hasn't somebody reacted in acid chloride in lab? Benzoyl chloride in lab? Who made a benzamide in lab? Reacted you made a benzamide? Benzoyl chloride? You used a base, didn't you? What base did you use? Two six? No? Devco, okay, there's two choices of bases in the chlorine lab. Either Devco or 2,6-lutadine. They're analogous to triethylamine. Devco it has two nitrogens and they're both tertiary. The lutadine is actually a pyridine. It's also sort of pseudo-tertiary. There's no H. None of these nitrogens have H's. They can lose an H and go neutral once they react. 2,6-lutadine and Devco are both just used to scavenge the acid that's generated. Okay. Would you want to use two equivalents of your aminofluorine? And have one equivalent just be thrown in the waste container as it acted as no, you'd be wasting half of your aminofluorine. So we bring in another base to pick up the HCl. Okay, why are acid chlorides key intermediates for acylation as opposed to carboxylic acid? Okay. I mean, you could say, why don't we displace this? Well, chlorine's a better leaving group, but in NAS chemistry here, just about anything can leave. The problem is, if you try to react this with a strong nucleophile, such as an amine or a Grignard reagent, a variety of things, you've got this acidic proton. And strong nucleophiles tend to also be strong bases. And a strong base is going to take this H and generate the anion. Nucleophile took the H. Game over, because this is not going to react towards a NAS reaction. Acyl substitution reaction. The anion, very unreactive. But the acid chloride doesn't have an acidic proton. And so your strong base / nucleophile is not going to do an acid base, it's going to do your nucleophilic addition. Okay? Electrons up and then back down, and you have your acyl substitution. So the acidic proton makes the carboxylic acid not good in many cases. The acid chloride is also just much more reactive, but that's an important consideration. The acidic proton can sometimes cause big problems and make the reaction just not work. We'll probably see that again. Okay, chemistry of acid anhydrides. What's an anhydride? It was not in organic 1 functional groups. It was not in the nomenclature video that you should be watching. We mentioned it before, but an anhydride is an oxygen bonded to 2 carbonyls. This is called a symmetrical anhydride because the R groups on each carbonyl are the same. Or this is called a mixed anhydride because the R groups are different. Benzene ring here, methyl here. Sometimes also called an asymmetrical anhydride. But often people just call them mixed anhydrides. Symmetrical anhydride. Now this here is acetic anhydride, because this is an acetyl group. And it's the anhydride that comes from acetic acid. I showed how to make here. Now the methyl carbonyl is just acyl, abbreviated AC. So you've got in the molecule 2 acyl groups bonded to an oxygen. And so this can be shown like this, 2 acyl groups on an oxygen. And so that's a common abbreviation. And this is called acetic anhydride. This is the one where I said is sold on the black market because you react morphine with acetic anhydride, you get heroin. Okay?
Have you ever made that?
Some of you have used acetic anhydride in lab, right? Okay.
Have you ever made heroin? Like just tried it out? I'm just curious to see what. No.
I have to have some morphine. I don't know. But it's done. Bucket chemistry. Get you a 5-gallon Lowe's bucket and some type of stirring and
You know how to do it, so I was just curious.
it's called bucket chemistry, okay? Why is it called an anhydride? Shown below, I'm going to show you a second version here, okay? Because it's really this, and you need two equivalents, and you get this plus what? What has to be removed from this to get that?
H2O.
Yes, if you just look at the elements here, what you do, no matter how many equivalents you have here, this is the acid. The acid self-reacts and eliminates water. When you eliminate water, you're dehydrating it. Okay, it's called an anhydride, and that's where the name comes from. We'll look at the exact chemistry below. Acetic acid, the anhydride is called acetic anhydride. Again, when you have that's the acetyl, or we can have acetyl chloride, or we can have acetic acid, or we can have, if this was just a nitrogen here, that would be called acetamide or acetamide. All right? So, anhydrides. How do you make anhydrides? Well, I've actually already seen one method. Okay? Please look back. Again, a lot of this chemistry just sort of cycles back around because you make them from carboxylic acids. Number two, a new way, is what I just showed you. If you take the acid to equivalents and if you heat it, pretty high temperature, maybe like 200 degrees, it'll start giving off water vapor. Okay? This is being formed, and then at 200 degrees, your water is going to be coming out as steam. And this will happen. And so you're dehydrating the acid, and the product that you get here is called an anhydride. But it looks like this. Now, I'm not going to do a full mechanism here, but what maybe is going on here? If we look at this, basically, the OH of one molecule is reacting with the carbonyl of another. And if you take this and you kick off this as a leaving group, and then if this oxygen is now bonded here, you see how this was one molecule and the O kicked the OH off of the other carbonyl? Now you could maybe do an acid catalyst. Is it strong enough to act as an acid catalyst? But you can do a mechanism here. We've already done all the steps. And you might do it on your own. Again, with this chemistry, I can't do every single mechanism. They're all the same. You need to do all the mechanisms yourself and work through them. Keep track of the proton. When does this proton get transferred? How do you ultimately get water? That's what's going on here. And heat sort of drives this. And it's in equilibrium. Okay, that is actually a true equilibrium. But if you heat this and the water is driven away as steam, then the water is removed from the equilibrium, and that moves everything this way. If you come back and you add in water, water will react with anhydride to give you the acid back. This method is only good for making symmetrical anhydrides. If you try to make a mixed anhydride this way, you're going to have a lot of problems. Imagine trying to react two different acids. 3 different products you could show here. Because this acid could react with itself, and that would give that. That acid could react with itself, and that would give that. But then you could say this could react with this. Okay? You can't say, okay, benzoic acid, I want you to only react with that guy. It won't listen to you. It's going to react with another of itself as well. So you're going to have a big mess there. So this is called what? A thermal dehydration of a carboxylic acid. It's best to only make symmetrical. Now you can do a chemical dehydration, I'm not showing that. I'm just showing thermal. Now cyclic acids, I mean not cyclic acids, but dicarboxylic acids I shouldn't say but these work very nicely. Internally, if you take these dicarboxylic acids like succinic acid, a common name, and heat it to a high temperature, it will dehydrate. One oxygen will displace the OH of another, and you can lose water there, and you can get a cyclic anhydride called succinic anhydride. That's actually a very common and easy reaction there, because it's internal. And so you often see cyclic anhydrides. We didn't do the Diels-Alder in Organic 1, but if you look back at the lab manual from Organic 1, there's a Diels-Alder reaction, and it uses maleic anhydride. Maleic anhydride is this, it just has a double bond here. And that double bond is a dienophile in the Diels-Alder reaction. If you still have your lab manual, I'll look back at that. It also mentioned that it's an anhydride, and that anhydrides would be seen in Organic 2. Well, today's the day. It talks about the blister beetle. Okay, reactions of anhydrides. Basically, one carbonyl is attacked, the other carbonyl is part of the leaving group. So this is very analogous to just having acid chloride. Okay? So see that as a chlorine here, as a leaving group. We only attack one. And so the nucleophile comes in, electrons up, back down, kicks that off. What is the leaving group? It's this carboxylate anion. Does it have any stability? It's resonance stabilized. But again, the leaving group leaves in the fast step, so it's not critical to be a great leaving group. But the fact that it's resonance stabilized does make this fairly reactive. But that's how they react. Now, your acid chlorides, though, are actually much better for delivering an acyl group. For example, if we wanted to make an amide here, we wanted to make this amide from the acid, we first typically have to convert this to the acid chloride, right? So 1 mole is converted to 1 mole, theoretically. Then we come in with ammonia, maybe 2 equivalents, and then we can displace that and we can get our amide plus ammonium chloride, right? And again, why not just react ammonia, the acid with ammonia?
It just plucks the acidic proton. It doesn't.
Right? We
Yeah.
talked about that. It's got the acidic gauge. So very often you need to convert to the acid chloride first. Okay? Well, you theoretically could do this. We could convert the acid to the anhydride. Then the anhydride can react with ammonia. Electrons up, down, kick this off. We get our amide, and then we can make ammonium acetate or something. Okay? Work through that. The problem is down here, you start with 1 mole of this, you're only going to get a half a mole of that. Because 1 mole of this is converted to 0.5 mole of this. Because this has 2 equivalents here. Or you can change this to 2 and change this to 1. But 2 moles of this react to make just 1 of these. All right? I'm just showing it in 1 and 0.5. And half of this is going to react to give half of that. The end result here is, would you rather start with 1 mole of acid and get 1 mole of amide, or would you rather start with 1 mole acid and only get a half a mole of amide? You'd rather do the top, right? Because down here, half of your original acid goes into the waste container after it acted as a base. You typically don't want to throw half of your acid in the waste container, unless it's cheap and not important. But very often, this is going to be the important fragment. So this is one of the drawbacks of anhydrides, is that half of it is a big portion that's going to be wasted. Of course, you can theoretically, you don't have to put it in the waste container. You can reclaim it, but that's going to take a lot of time and effort. That's a better approach. So acid chlorides are much more versatile. But there are some cases where you would want to use an anhydride. For example, maybe you want to convert morphine to heroin. Well, acetic anhydride is much better because acetic anhydride is much more stable than this. This will survive a longer time. You can store it easily. Okay? This is very reactive. You open up the bottle, it's going to start giving off HCl. Because there's water in the atmosphere. And these react to give something plus HCl. This doesn't react with water quite as readily. Okay? Can be useful in some cases. Okay, and you can show products down below. Acetic anhydride, right? Cyclic anhydride. It's important because the leaving group really doesn't leave. Most of, before we've used amines. Can we use alcohols as nucleophiles? Sure. Try these on your own. In some cases, the acid chloride is not stable. For example, with 3 fluorines here, that's not stable. But the anhydride is. And you can use it for your acyl substitution. This is also not stable with just an H here. But the mixed anhydride is often used. Now with mixed anhydrides, we have to ask. See, if it's symmetrical, it doesn't matter which carbonyl you attack. They're the same. But mixed, they're different. The question is, if we had a nucleophile, and it's the same here, which carbonyl is the nucleophile going to attack? Left or right? And this is a good consideration.
Right. It's less. It's more.
Why the one on the left?
Because you'd easily be able to get the hydrogen.
Because you can what?
Like you'd easily go like deprotonate later.
Deprotonate. No, we're not going to lose that hydrogen. Or talking about this hydrogen? That hydrogen's not going to ever be deprotonated. We'll lose nitrogen.
Less hindered? It's less hindered?
Less hindered, yeah. That's in terms of sterics. What about electronics? This is an H, this is an sp3 carbon. What is the electronic nature of sp3 carbon?
It's donating.
Donating, right? sp3 carbon donates. That's why tertiary carbocation is more stable than the secondary. So which carbonyl, we're asking, which one has the most partial plus?
The one
The
on.
one on the right. No.
one on the left, because the one on the right, the partial plus is being diminished because it's got a rich friend. Okay? Electrons are being moved here. More reactive here. And I've actually used this mixed anhydride before, and it reacts very nicely to give. It reacts here. Electrons up, back down. Kick that off. That's the leaving group, right? And we're going to get product here. That's the leaving group, right? Something took the H in your mechanism. Trifluamine, you make that ion pair. We make the amide. That's called a formamide. It's the amide of formic acid. Formamide. Okay, these reactions, I can't go slow here and do every little detail of every reaction. I'm trying to get you to understand. We just did it. You've got to go sit down and make sure you see what's going on here, okay? And it's all just straightforward. We're doing the same thing over and over. But I sense that every time I put it up there, you guys are going, what's going on here? I'm trying to write it down. What's going on here? It's okay. We don't have time to, all right? You've got to almost not even hardly write it down. You've got to go do it. Okay? Where did all this come from? You got to do the mechanism. Well, we've already done the mechanism. All right. Again, that's a mixed anhydride that reacts very nicely to give you the formamide. Why is it called a formamide? Because what's the name of this acid?
Formic acid.
Formic acid. We made an amide. It's essentially an amide of formic acid. Because instead of the acid, it's now an amide, but the nitrogen has stuff connected to it. So that's kind of the verbiage we use. It's the amide of formic acid called a formamide. The amide of acetic acid is called an acetamide. What's the amide of a benzoic acid called? A benzamide. Get the idea? And those are sort of the most common. Okay, what do we got going on below? Kind of looks like an anhydride. It's actually not, though, because in hydride you would have R group, R group. We got an R group here, but this is almost like an ester. It's not exactly an anhydride, but it's, for us, what we're doing here is essentially an anhydride. Which carbonyl will we attack? Left or right?
To the left.
Well, this has a pretty strong donating oxygen. That's a resonance donation towards the carbonyl. That's going to be a stronger donation than just inductive. Okay? What's the nucleophile? What do we have over here? I got lone pairs here and here. What's going to attack a carbonyl? What's a better nucleophile? Neutral oxygen or neutral nitrogen? Neutral nitrogen, yeah. Here's your nucleophile. Over here. Electrons up, back down, kick this off. The carbonyl on the right is more electrophilic because the one on the left has an electron donating oxygen. I've used mixed anhydrides like this before and they work very nicely to give. What type of product are we going to get here? It's going to be the acetamide. By the way, that's called morpholine. You don't need to know that. It's the acetamide of morpholine plus what? Going to blow your mind here. Plus what? plus CO2 plus what? Plus ethanol. Everybody got that? Now, what did we form here? Was that the leaving group that we lost?
Yeah.
Okay. How do we get CO2 here? Anytime you can make a pi bond and kick off a leaving group, easy to do. Have we said that before?
Yeah.
And what does that give?
CO2 with
CO2 plus O ethyl minus. That's a pretty dang strong base. At some point, something takes this H. Triethylamine could take it. I'm going to say that ethoxide is going to take it. Okay? And triethylamine really did nothing here, other than maybe act as a catalyst. And I'm not willing to describe how maybe that happened. Important part is, do you see how CO2 could have been formed? Because anytime you can make a pi bond, okay, these types of things will happen. All right. Did you see that coming? All right. And so the fate of the H here is, I'm telling you that this is going to take that H eventually, and you're going to get ethanol. So the acetamide there, those mixed things work pretty well. Chemistry of esters. Esters, we've already synthesized esters, see before. We've already shown synthesis of esters. Okay, esters. Important to state this. We've cut acyl chlorides and anhydrides. Both of those tend to be just reactive intermediates in lab. You're never going to find an acid chloride. Neither of these are going to be found in nature. So they both react with water. This reacts even faster, but this will react with water. Just a little slower. Not going to find these in nature. These are never going to be drugs or end products. These are reactive intermediates in lab, reagents in lab. Once we get to esters and amides are end products because they don't react with water directly. You can find esters in nature. You can find amides in nature. Okay? But you can hydrolyze esters back to carboxylic acids. Any acid derivative can be hydrolyzed back. But it requires more than just pure water. You're going to have an acid catalyst or a stronger nucleophile. Here we're using an acid catalyst. This is water and H+. Take an ester, we can hydrolyze it to the acid. Plus ethanol. This is just a reverse of the Fischer esterification. Remember we talked about the equilibrium before? How do you drive it? Fischer esterification is taking an acid and going that way. We're just coming the other way. We're about out of time here. Let's see how we can finish up. We've already covered that mechanism, though. Again, you've got to sit down and do it on your own. What's the first step of this mechanism? Protonate carbonyl. I gave you an entire page about the strategy there. Protonating carbonyl, acidic conditions. Please be looking ahead. We've got to move ahead, guys. And I've tried, and I won't keep harping on it. But the mechanisms here we've already covered. You've got to sit down and work out the fine details on your own. Because it would take me 15, 30 minutes to get you to recognize one fine detail. We don't have that much time. You've got to recognize the fine details on your own here. How we can do carbonyl chemistry and replace one group with another. Very often we have to keep track of the proton. All right? Have a good day, guys. I didn't mention IR, but I sent that email yesterday. Please be looking at the email.